So today I am doing algebra, third part of the algebra, and in this chapter I will do the matrix chapter. Matrix and related to that is determinant. So matrix, these are it is an m by n array, m by n array. So m is the row number, then n is the column number, then we say it is a matrix. So this is the matrix A. This is a 3 by 3 matrix. 3 by 3 matrix. So row number is 3, column number is 3. This is 3 by 4 matrix. 3 by 4 matrix. So row number is 3 and column number is 4. So you know these things, and its entries are Aij. Aij we say. This is Aij. Aij. So ith row and jth column. So two suffix are there. One is first one is I. First suffix is represents the row number, and second suffix is column number. So here if we say A2 A32 A32, this is row number is 3, column number is 2, and in this matrix A32 is -5. Or if you say A33, or you may say A13. 13 is row number is 1 and column number is 3, that is A11. So these are the entries Ij. So this is rectangular matrix. When m is unequal to n, then it is rectangular matrix. It is square matrix when it is m equal to n, then it is square matrix. Then diagonal matrix. Diagonal matrix means diagonal elements are other than diagonal elements are all 0. That is diagonal matrix. Then zero matrix, all elements are 0. And identity matrix or unit matrix, diagonal elements are 1. Singular matrix. So every matrix, every square matrix means m equal to n. It is associated with determinant. Determinant, determinant of order n is n by n determinant, and you know this things. So with the help of determinants you can find a value. Matrix is a different thing. Matrix is just an arrangement of elements, but determinant we have to find some values. So it may be real number or it may be complex number. We can compute the values. And so for rectangular matrix we cannot find a determinant, but for square matrix we can find determinant. And this determinant, if this determinant is 0, then A is called singular matrix. If determinant A is not equal to 0, then it is non-singular, like that. So symmetric matrix, this is the definition. So Aij is equal to Aji. Then skew symmetric matrix. Skew symmetric matrix is of opposite sign. Then Hermitian matrix. A square matrix is a Hermitian matrix. Aij equal to conjugate. These are here entries are conjugate numbers. Complex numbers. In ordinary case we consider this as real numbers, but sometimes we may consider this thing, and then we can define Hermitian matrix. So it is Aij is equal to conjugate of this. Then diagonal elements of a Hermitian matrix are real. Then skew Hermitian matrix, this is negative of this conjugate. And in this case diagonal elements are purely imaginary. Then nilpotent matrix, actually this is I am just writing it because one question is related to these things. So nilpotent matrix, some options are there, if it is nilpotent matrix or not, if it is idempotent or not, if it is involutory or not. So I am just defining these things. So nilpotent matrix, it is a to the power 4. If there exists some integer n, then this is equal to 0, then we say it is a nilpotent matrix. Idempotent matrix is if a square of this matrix is itself, or you may say A into A inverse is not that. Idempotent matrix, so square of this is equal to A. Then involutory matrix, this is A square equal to I. Or you may say it is matrix is the own inverse is its own inverse. Then orthogonal matrix is this one. Then transpose of matrix is just write rows as columns and columns as rows, and this is the. Then conjugate transpose, if these are complex numbers, then we can find conjugate transpose. So conjugate transpose is, first thing you have to take the transpose, and then the entries we consider this as conjugate of this. So if it is say if a21 is says a21 say 3 plus 6i, then here we will write a2 here we will write a2, this will be 10 taking after taking transpose. So if it is 3 plus 6i, here we have to write 3 minus 6i. So every element we have to take conjugate. Then unitary matrix, just like orthogonal matrix, unitary matrix is a into this is a to the power h. This is conjugate transpose. So product of the matrix and its conjugate transpose is equal to I. So we are just defining these things. Then you know these things. I am just reminding you. Adjoint of a square matrix. This is to find the inverse. This is necessary for finding inverse. When you did the determine how do you do this? This definition is like this. So cofactor. So summation aij, this one. This is a cofactor. So this cofactor, we consider a cofactor of this, then take the transpose of this, and this we say adjoint of A. And adjoint of A into adjoint of A, you can see these things. So A into adjoint of A, this is equal to determinant of A. So inverse of matrix. So inverse is, with the help of this we can find, we divide by determinant of this, and this is the inverse of matrix. So A inverse is equal to 1 by determinant A into adjoint of A. Then characteristic equation. So characteristic equation of square matrix. So A is a square matrix of order n for a scalar value lambda and nth order identity matrix. Then A minus lambda we say this characteristic matrix of A. Then if this is a for simplicity we are considering only the 2 by 2 matrix, and this 2 by 2 matrix A is equal to 1 2 3 minus 1. So this is a square matrix of order 2, and characteristic matrix will be this one, 1 minus lambda 2. So because identity matrix is 1 0 0 1, so it is 1 minus lambda 2 3 minus 1 minus lambda. And since A minus lambda is a square matrix, so we can have the determinant. So this determinant is equal to 0 is the characteristic equation, and we get a polynomial in lambda. So like this is polynomial in it is a quadratic equation with degree 2 in lambda. So then we solve this for lambda, and we get solutions, n solutions we will have. So here if it is second degree, then we will have 2 solutions. If it is third degree, then this will have 3 solutions, like that. So for nth degree, nth order matrix, we have this n number of roots. Now if lambda 1 lambda 2 lambda n are n characteristic roots of this, then any square matrix A and its transpose have the same eigenvalue. So these are called eigenvalue or characteristic root, and these are the properties of this. So the product of the eigenvalues of matrix A is equal to this. If one of the eigenvalue is 0, then matrix is singular. Then if lambda 1 lambda 2, so n eigenvalues we will have for nth order matrix. So then for Ka we will have this k lambda 1, k lambda 2, k lambda 3, etc. Then a to the power m has this one. Then a to the power minus 1, we get the reciprocal of this, so etc. So these are the properties, and these are the characteristic roots of Hermitian matrix are all real. The characteristic roots of real symmetric matrix are all real. The characteristic roots of a skew Hermitian matrix are all either purely imaginary or 0. The characteristic roots of a real skew symmetric matrix are either purely imaginary or 0. Then characteristic roots of a unitary matrix, also of an orthogonal matrix, are of unit modulus. So this one, and this is another theorem. It is called Cayley-Hamilton's theorem. So every square matrix satisfies this characteristic equation. This is called Cayley-Hamilton's theorem. So let's explain these things. Just do it. Let's see these things. So what we have discussed. What we have discussed. So matrix. So this is a matrix. This is a matrix is say 2, 6, 3, 1, minus 1, 2, 5, 0. So this is a 2 by 4 matrix. So its transpose is the what? So this is, if it is A, this is A, then transpose is A T, we write it as A T, and this is equal to, this is 2 by 4 matrix, so this will be you write rows as columns, so it is 2, 6, 3, 1 and minus 1, 2, 5, 0. So this is AT. This is AT transpose. This is 4 by 2. And if it is some complex numbers are there, say, so say B is equal to say it is say 2 plus 3i, then 6 plus I, 6 plus I, then it is say 5 minus I, so it is minus 2i. Then if we say BT will be what? We take the transpose. Transpose will be, we are writing 2 plus 3i, or we can do these things. Say we take, say, so here I am writing 6 plus I, 6 plus I plus, sorry, not this one, so it is minus I, and here it is minus 2, and third column we say it is 1 plus I. Then this is 2 by 3, and here columns will be 6 plus I, this one is 6 plus I, then it is minus I, and it is 5 minus I, then it is minus 2, 1 plus I. So this is BT. This is for complex entries. Then BH, what will be BH? BH is conjugate transpose. So conjugate transpose, it will be, so first I am taking the transpose, then you take the conjugates of this. So this will be 2 minus 3i, then 6 minus I, then I, then this is 5 minus I, then it is minus 2 will remain same, and it is 1 minus I. So this is pH. So this is pH. So this is conjugate complex. Then so symmetric symmetric matrices are those symmetric matrix. Say it is, this is symmetric matrix. We are considering only real entries. Say it is 2. We are considering only square matrices 2, 3, 0. Then it is first you write the diagonal elements. So it is 5. Then it is 6. Suppose it is 1. Then here you have to write minus 1. Minus 1. This is 0 and this is minus 3. So this is symmetric matrix. This is symmetric matrix. Aij is equal to Aji. And skew symmetric matrix will be skew symmetric matrix. This is symmetric. This is symmetric. Then skew symmetric matrix is this one. Say it is. Oh, sorry, not that. Just wait. This is symmetric. So symmetric is Aij is equal to this one. So minus sign. This is symmetric. And skew symmetric matrix will be diagonal elements will be J. Sorry. So it is 0, 0, 0. Then will be this one. This is minus 1. So it is minus 4. This is 3. Then this will be 1. This is 4. And this is minus 3. So this is skew symmetric. This is skew symmetric. This is skew symmetric matrix. Then Hermitian, for Hermitian you have to consider complex numbers. Then Hermitian will be the same thing. For Hermitian matrix, this will be purely imaginary. You yourself check it. Then let's come to rank of matrix. So rank of matrix. So rank of matrix, suppose, let us explain these things. So rank of matrix, suppose A is a matrix, say A is a matrix, say A is a matrix, say its entries are say it's not coming, just do it. Just do it. So rank of a matrix, it is this submatrix, the submatrix which is having the minimum value. This is say A is of order, say it is say 4, 3, 2, 0. So it is minus 6, 1, 5, 2. So this is a matrix of order 2 by 4. Then rank is that, so it is having some submatrices. So 4 is a submatrix of order 1. Then 0 is a submatrix of order 1. 4, 2, minus 6, 5. This is also submatrix. This is also submatrix. So it is a square matrix. Square matrix, and take some entries. Take some entries from this. In a row, we are in the first row we are considering 4 2 element, and in the second row we are considering minus 6 5. So these are submatrices. So rank of a matrix is defined such that determinant of this. So if this is a submatrix, say A1, so this is A1, then determinant. So determinant of A1 is not equal to 0. So if we have determinant of A1 equal to 0, then we say it is not of rank 2, because it is of order 2. So every matrix, when we are given some matrices A, m by n, then m is the minimum. Suppose m is less than n. Then in that case, we define R is a number, R is less than equal to n. R is a number, and this R is such that this A is a submatrix. A say A1 I am saying. So A1 is of order R. So determinant of A1 is unequal to 0. And if A1 A2 is of order say R plus 1, then determinant of R plus 1, so determinant of A2 is 0 for all R plus 1. So in this case, in this matrix, so we are having in this matrix, so this is 2 by 4 matrix. So we are having submatrices. How many submatrices we will have here? We will have 4 3 minus 1 minus 6 1, or 3 2 1 5, or 2 0 5 2, or 4 2 minus 6 5, etc., etc. So we will have altogether 4C2 we are getting. So 4C2 means it is 6. So 6 submatrices of order 2 will have. So we will have 6 submatrices. 6 submatrices we will have. So all this must have determinant. So determinant of all these submatrices must be 0. If they are 0, then we say this is of rank not R plus 1. This is of not rank not R plus. Suppose we are writing all these things. We are writing say all these things as 0. This one. Suppose all are 0 here. All are 0. So this is all are 0. So this is 0, this is 0, this is 0, this is 0. So all are 0. Then obviously we will have all determinant of order 2 will be of submatrices will be 0. So 4 3 0 0, this is 0, 3 2 0 0, all are 0. So this is the rank. So rank means, so every there exists some submatrix of order R which is not equal to 0, whose determinant is not equal to 0, and every submatrix of order R plus 1 must be 0. And this determinant, these things here, So whenever there is a matrix, say A is a matrix, A is, suppose this is equal to, say, in standard form, what you write, and say A11, A12, etc., etc., A1, n columns are there, then A21, then A22, then A2n, then this dot dot dot. We don't know how many m's are, how many n's are there. So last you write AM1, then AM2, then AMn. So this is an m into n matrix. So by some transformation, we say elementary transformation, we have like this. By some transformation, this is equivalent to some matrix, say we are writing here, say A11, we write dash here, A12, we write dash here, then A13 dash like this, some values, A1, 1n, A1n dash, then A22, A21 dash, etc., etc., right, these things. Then you write dash, these are all dash, then you write AR1, AR1 dash, then AR2 dash, then AR3 dash, etc., etc. Then all are 0 here, other elements all are 0. So these are 0, 0. So by some elementary transformation, we are not discussing this thing, we are just saying these things so that you can imagine this. You can imagine this. So all are 0. So all are 0 here. Then yes, then we say there are some elementary transformation to make it equivalent to these things, and then this is of non-zero entries. Non-zero entries of this R row matrix, and this is of rank. Then we say if we can eliminate all these things to 0, eliminate all these things to 0, then and other things cannot be eliminated. These R rows we cannot eliminate, and then this matrix we say this rank. So rank of A m into n. So its rank is equal to R. So just I am explaining these things. You don't you need not go in depth of this. Just I am using so that you can try the objective multiple choice questions. So these things. So this is the rank of the matrix. And now we will discuss the some. Let's see your question patterns. We will see. Some question patterns. Just wait. So this is submatrix. We have discussed these things. Then rank of matrix. So this is rank of matrix. So these are the questions. Now this one you see, A is a square matrix of order n and k is a constant. Then k a to the power t. This we are having from this one. And one thing you can see. Suppose. So these are the properties of characteristic roots. So these are eigenvalues or eigenroots, etc. And one thing you know these things, but I can. So if suppose A is a matrix is equal to say for simplicity I am considering only this one, 6 to say minus 1 5. Then what is determinant of this? Determinant of this is equal to 30 minus 30 minus 2, so it is 32. This is 32. And suppose you are doing say 3a. So 3a matrix is what? 3a matrix is, this is 18. We have to multiply all entries by 3. So it is 6, then minus 3, and this is 15. And what is determinant 3a? Determinant 3a is, so how many 3's are we are multiplying? So it is 3 into, so 18 into 15, so 3 square into 6 minus 6 into 5 minus, again it is 3 square into 2 into minus 1. So it is and this is 3 square. So this is equal to 3 square into determinant A. So this is so when we now use in this property characteristic roots is, so it is determinant A is product of the all eigenvalues or characteristic roots. This is product. So K is a matrix, then its product Ka, determinant of Ka will be what? K to the power n into determinant A. So its eigenvalues, this will multiply, then lambda 1, lambda 2, lambda n, we know this is equal determinant A, and n case must be there, so as to get this K to the power n, because we need K to the power n, because determinant of K is K to the power n into A. So this is one property. Then A to the power m. So this. So we are applying this here. A is a square matrix of order n and K is a constant. Then Ka transpose of Ka. Transpose of Ka is what? Transpose of Ka. You can just test it. Yes. I can just test it. So it is Ka. So A is equal to say, so it is 2 minus 1 5 0 1 3. Then what is 80? Ka is, so Ka is K to 2K, then minus K, then 5K, then 0, then K and 3K. So this is K. Then when we take transpose, this will go as column is rows. So again you take out K and it is again transpose. So our answer is A. So this is very simple. Okay, this thing. Next, second one you see it. A, only correct statement about A is A square. You have to compute the value. It's very simple. So A is only correct statement about A. So you multiply this, multiplication of the matrix. I think you have got the familiar multiplication of A. So you try to multiply this. So A square is what? A inverse doesn't exist. A inverse doesn't exist. Is it true or not? A inverse must exist because this is A is non-singular. A inverse, it is false. A inverse exists because this determinant of A is what? 0, 0, minus 1 into 0 minus 1 into 0 minus 1. So its determinant is not 0. So A is non-singular. So A inverse must exist. A is not null. A is not null. Null matrix is what? Every entry must be 0. A is not null. So A is not equal to minus I because identity matrix is what? I means I is equal to what? I of 3 is diagonal elements are 1 and 1 and others are 0. So all our elements are 0. So 0, 0. So this is identity matrix. This is identity matrix. And A square. When A square you try, you multiply this thing, set A square. A square when you multiply, what will have? A square. So A into A. So A into A. So A square is, so it will be 1, 0, 0 minus 1. So this into this, A into A. So it is 0, 0 minus 1, then 0 minus 1, 0, then minus 1, 0, 0, then and it is 0, 0 minus 1, 0 minus 1, 0 minus 1, 0, 0. So when you multiply, what you do? Then this is 0 into 0, 0 into 0, minus 1 into minus 1. So first element we will have it is 1. So this is equal to, this is 1. Then 0, 0, 0, 0, this is 0. So this is 0. Then you multiply this, you will get this at 0. So only diagonal element are 1, 1, 0. This is again 0, this is again 0, this is 0, 0. So we have it as option. Option is your just let's erase it. So this one is next. For this I have defined these things: nilpotent, orthogonal, involutory. So for involutory, so idempotent. Idempotent means I minus A. Involutory means orthogonal. So I minus A is an idempotent matrix. A is an idempotent matrix means A square is equal to A. So this is the definition: idempotent. Idempotent. So A square is equal to A. This is the definition. So what you have to do? Idempotent. So let us multiply this. So I minus A. If you say I minus A into I minus A, I minus A. So this is equal to I into A, I into I minus A into I minus I into A plus A into A, A into A. Then I into I identity matrix is I. Then A into I, because I A is A, because A multiplication is not commutative. A B we cannot write as B A, but A I is because it is identity element, so it is A. This is again A, and A square because it is idempotent, so it is A square. So this is A. So this goes and remains. We have I minus A is equal to I. So what we are having, I minus A square is equal to I minus A, I minus A. So it is a definition of idempotent. So our option is this one. Next you see eigenvalues of this is Hermitian matrix. It is purely imaginary. So when we defined Hermitian matrix, we have mentioned these things. So for real eigenvalues are real, so it is for Hermitian and real symmetric. So symmetric matrix, it may not be real number, real entries, so it must be real symmetric. So we cannot write symmetric here, so our answer is Hermitian. Then the rank of a matrix with n rows is R, then the number of zeros in the normal form, that is a normal form, that we explained, that other rows become 0, that is a normal form. By elementary transformation, we make the n minus r rows 0, that is a normal form. So number of 0 rows, so this is 0 rows, so this is n minus r. Then the diagonal elements of a Hermitian matrix, it is given in the property. Then the inverse of matrix, you have to compute these things. It is 2 by 2 matrix, so inverse of matrix is, you see this thing, you try this, 5 2 3 1 by 1 you can do it, because it is only 2 by 2 matrix. So 5 2 into 3 1, so 5 2 into 3 1 into minus 5 minus 2 into this, so that must give you I. So this gives you I. So this one is, so this is 5 5 2, this is 5 2, and this one is 3 1 into, this is minus 1 2, and this 3 minus 5. So how much you will have? So 5 into minus 1 is minus 5 plus 6, it is 1. Then 5 into 2, it is 10. Second this element 5 into 10 is 10, it is 0, so it is 0. Then 3 into minus 1 is minus 3, so it is also 0, and 3 into 6, it is 1. So this we have identity matrix. So it is by trial and error method we will have it. So next one is eigenvalue of square matrix A. This will come from property 2A, it is you have to multiply by lambda. Then rank of matrix, so to find rank of matrix, because it is only of order 3, so you just see, it is, if it is singular, then it cannot be, if it is singular, then it cannot be rank 3 if it is non-singular. So you just find the determinant of this. So what is determinant of this? Determinant of this is, so you can write A is equal to 2 into 9, it is 9 plus 8, 2 into minus 9 plus 8, so it is minus 2, and 0, first column you consider plus 0, then with 2 this minus 2, minus 2 plus 3, so it is plus 2, so plus 2, so this is 0. So we are having this is, so this is the matrix. So according to the definition of rank, so it cannot be of rank 3. Then you consider any one submatrix of order 2. So suppose we are considering 2 1 3 0 3. So this will give you 6 minus 1 6 minus 0. So this is a non-zero value. So this is the maximum number which is having a non-zero submatrix of order. So this order, it is 2. Then next one is rank of fifth order identity. Identity matrix means it is diagonal elements are 1, so its value is 1. So it is 5. If A is the nth order matrix, then determinant 5 is, so 5A. So you when you take the determinant, so you from every row you take out 5. So n, from n row you are taking out 5 to the power n, and other is this one. So your answer is this, 5 to the power n, determinant A. Then A is a symmetric matrix of order 3, then determinant A is a skew symmetric matrix of order 3. Then determinant A is 0. It is actually you have to see there is not such theorem. You can for order 3 for you can try this one, number 12. So it is a skew symmetric matrix. First you write one skew symmetric matrix. So for, your diagonal elements will be 0. First element is 0, then you write is A 1 2, next is A 1 3, then this element will be minus A 1 2, this is 0, this will be A 2 3, then next this will be minus A 1 3, this will be minus A 2 3, this is 0. Then you find the determinant. So 0 is 0, then A1 2. So A1 2 into 0, this one. So determinant will be is equal to, this is 0, then minus A1 2, you can have A1 2, then we'll have this first, it is 0, then plus A1 3 A2 3, so it is A1 3 A2 3, then next one is plus A1 3 into A1 3 into A1 3, so it is A1 2 into A2 3, A1 2 into A2 3, so answer is 0. So these are 0. So A is skew symmetric matrix, so order is 3, determinant A is 0. Next one is this one. A is this, A square is AT AI. This you have to compute this. You have to compute A square. It is simple. But you consider suppose A square means A into A. So what is the first element? So first element will be 4 into 4 16, then minus 1 4 into and minus 1 into 3, it is minus 3, so 16 minus 3, then minus 4 into 3 minus 12, so 16 minus 15, this is 1. Then second element is 4 into minus 1, 4 into minus 1, minus 4, then 0, then plus 4, plus 4, 3 0 4. If you consider this 3 second row and first column, so 3 into 4, it is 12, plus 0 minus 12. Let's see what you get. A square, so A square is, this is 4 minus 1 minus 4, 3 0 4, then 3 minus 1 minus 3. 4 minus 1 minus 4, 3 0, 4, 3, minus 1, minus 3. So if you multiply this, what you will have? So this is equal to, so what is the first element? This is 4 into 4, 16, then minus 1 into 3, minus 3, then minus 12. So this one is 1, first element is 1. Then second element, 4 into minus 4, 0, plus 4, so this one is 0. Then third element is 4 into minus 16, then plus 4, minus 16, minus 16 minus 4, it is minus 20, minus 20 plus 12, minus 20 plus 12, how much it is? Minus 20 plus 12, minus 8. So this one is minus 8, minus 8. So first row we are having this. So so this cannot be I, this cannot be A, and this cannot be AT, because if it is AT, then this first row must be 4TT. So this is not happening. So our answer is none of this. Then next one you have to just simplify this. Next one, it is a square is equal to 8a plus ki. So find a square. What is a square here? A square is number 15. A square is 1 into 0, 1 into 1, 0. So first element is 1, 1 into 0 into minus 7. Second element is 1 into 0, 1 to 0, 1, this is 0, minus 1, 7, 1, 0, minus 1, 7. So is equal to, what will be a square here? So a square is 1 into 1, 1 into 1, so first element is 1. Second element is 1 into 0, 1 into 0 plus 0 into 7, so second element is 0. Then third element is this second row, minus 1 into minus 1, 7 into minus 1, so it is minus 8, minus 8, and minus 1 into 0, 7 into 7 is 49, so this is 49. So this is a square, and a square is equal to 8a plus ki, 8a plus ki. So this is equal to 8a. 8a means 8, 0, and 8a. So it is 8 minus 8 to 56. This one is 56. This is 8a plus ki means k 0 0 k. So 8 plus k. So what we have to have in the right hand side is 8 plus k. 8 plus k is equal to 1, and this is minus 0 is 0, then minus 8 is minus 8, then 49 is equal to 56 plus k, and this will give you a is equal to this one. So this is, or these things I have selected from your previous question papers. On the basis of this, I have solved these problems that I have got it, and on basis of this I am writing some theory parts. You go through these things, the definition. I think these are sufficient, and if you find any difficulties here, you can call me and we can discuss these things. So this is rank, sorry, this is matrix, and determinant is very simple. You have got all these things. You can review these things from any algebra book. You have studied these things in first semester. So these are the properties, and with the help of properties I am doing these problems, and these are the questions. These are the questions from this. So this is 1 2 3 4 minus 1 7 2 4 0. Its value they needed. So it is minus sign. Actually it is minus. This is equal. Oh yes, it is coming. Yes, it's equal. So you find the determinant of this, and you will have to, and this property is here. So 1 2 3 2 4 6. So R1 equal to R3. From this property directly you can write it is, this value is 0. Two similar rows or two similar columns or multiple of one row. So this becomes 0. This will come from the property. Then this also I have solved these things using property. I am doing this. So its value is this one. Then this one, this determinant is its value. This also we are using property. So you take out this minus 3i. Then you take out this minus 3i. We are having the same column, 1 minus 1i, 1 minus 1i. So value is 0. So x is 0, y is 0. We have to write x and y, and we have to write in complex form. So it is 0. X real part is 0, imaginary part is 0. So this much is for you. I have completed now. Here I have completed this one algebra part. Okay. So we'll discuss these things. You go through all these things. We'll discuss it in classroom. So you ask, you find some other questions, then we can discuss, so that we can discuss these things. So thank you.